Look at alcohols here in general. We've already talked about alcohols, and we've already shown you how to make a bunch of alcohols with SN2 and SN1 chemistry. Here are some of the most common alcohols. Here's methyl alcohol or grain alcohol. When wood ferments and decomposes, it creates methanol here. Methanol is toxic. What does LD50 stand for? I think you've probably seen that in some classes talking about toxicity. What's LD? Lethal dose, right? That can kill 50% of a population. And these are actually LD50s for a whole person, okay? A 70 kilogram person. So 10 mils is not much. That's just a couple ounces. In fact, the first thing that'll happen if you ingest that, you'll go blind, and then you'll have some real issues there. What about this one? This is ethyl alcohol or ethanol or grain alcohol. If you ferment starchy compounds, starchy material from nature, fermentation of yeast will create ethanol, which has antibiotic activity. You can go up to about a 15% solution of the fermentation broth that will have ethanol, and the yeast produces it to kill off other microorganisms that might try to grow on that material. So ethanol, alcoholic beverages, right? So that's where that comes from. Much higher LD50 value, so it's not as toxic. 200 milliliters is quite a bit. Of course, there's a lot of other bad effects with that. And this is the dose that kills you, right? So before you get to that point, you have inebriation and a number of other problems. And chronic usage, of course, has cirrhosis of the liver and a lot of other damaging health effects there. And then we've got rubbing alcohol, isopropyl alcohol. Boy, don't mix those two up, right? Rubbing alcohol is a very different thing than ethyl alcohol or methyl alcohol, but it is quite toxic, okay? It is antiseptic to the skin. It has a cooling effect, so it's used clinically and in the household, whatever, but be careful with that. Another one to be careful with is phenol, the aromatic alcohol, right? That has a lethal dose, 5 grams. We switch over to grams because it is a solid material. This was developed by Joseph Lister, the famous Scottish surgeon who used it in the operating rooms for the first time as an aerosol spray to cut down on infections in operations. Now, speaking of operations, we'll talk about ethers, also diethyl ether that's developed as the first general analgesic compound to put people under for operations. So these simple compounds have a lot of usages. And so I'm emphasizing what toxicity right now, but alcohols are all over the place in nature, okay? And they're one of the most abundant, important functional groups. They're in the sugar molecules, in fact, right? They're in DNA. They're in amino acids. So these simple ones on their own, yeah, can be quite toxic and have different effects. By the way, every compound has a toxic effect, right? Even water. Can water kill you? Yeah, a lot of people drowned every year, right? That's more of a mechanical effect. These all have specific effects on receptors in the body, which is kind of interesting. First, we look at maybe, we've talked about this before, the properties, water solubility. All these are infinitely soluble except phenol. I don't have the solubility of that. The first 3 are all infinitely soluble. Well, what about octanol? Straight chain N-octanol. That's not soluble. We'll see a tiny amount of solubility associated with that because the long hydrocarbon chain here getting larger by the hydrophobic effect, it's harder for water to solvate that part of the molecule. So molecules can have this amphiphilic effect where part of it is acted that way. Now we'll get into reactivity, of course. We'll talk about conversion of alcohols to different things and the preparation of alcohols. Let's see. The other compounds to introduce, of course, are the ethers. They're also in this chapter, diethyl ether. The first general analgesic compound, like I said, a painkiller, can also put you under for an operation. Person won't feel any pain. Discovered in the mid 1800s, accidentally actually, by a medical student at Harvard, William Morton. Was at a party once where they were actually inhaling this material, believe it or not. That was a thing, I guess, in the mid-1800s. He inhaled a bunch of this from a paper bag, and he was dancing around the room. I guess it was some sort of party. He hit his leg on a sharp corner on a coffee table and cut a big gash in his leg. And he kept dancing around and thought, oh, this is really fun. Well, they patched him up, but the next morning he got thinking, now, why didn't I feel any pain? I cut this big gash in my leg. Ah, maybe it was the ether we were inhaling. He took that idea back to Harvard, believe it or not, and they started using this for operations. And that's the first general anesthesia agent. The problem is, it's very flammable. It caused a lot of bad fires in operating rooms. You have a lot of spark sources in an operating room. So if you have this as a material you're giving to a patient, that can be a problem. Plus, it does have an LD50. It does have a toxicity level. So you can put the person out to the point where they're actually killed that way. So very dangerous. Most analgesia agents now are polyhalogenated ethers. Haldane, maybe you've heard of some of those. Anesthesiologists use those. But it's the same effect there. It denatures different enzymes in neurons and shuts down the neuronal signaling pathway, shuts down the pain pathway, and of course consciousness as well. So simple compound, but very profound activity and effects there. We'll also look at epoxides, which are the little three-membered ring compounds that relate to ethers as well. We'll see a lot of reactivity with epoxides, but not so much with ethers. Okay. Now, speaking of reactivity, we know how to make a lot of these alcohols, right? SN2 reactions. Okay. Primary and secondary, we can do that with hydroxide, and that's a great reaction. If we want to make tertiary and secondary, we can't use strong charged nucleophiles. They're too basic, right? We get a lot of elimination here. Here we use not SN2 chemistry. We use what? We use SN1 chemistry. We can make a lot of those that way. We can also make the ethers, the corresponding ethers here, if we use alkoxides. So these are R groups with an oxygen here. This is the conjugate base of an alcohol, right? And then we can put on whatever ether we want to make. And again, that's an SN2 reaction. Primary and secondary work fine there. What if we want to make the corresponding tertiary and secondary ones? Well, then we just use alcohols themselves, right? Again, SN1 chemistry here, and we get, all sorts of products like that. So we already know how to make quite a few of these. Now, when we think about reactivity, though, of alcohols, we've got some limitations here. Can we use alcohols with nucleophiles to do different reactions? Now, how good of a leaving group, the question is an alcohol. Halides are very good leaving groups with electron-rich nucleophilic reagents. But how about an alcohol? Well, we can draw this, right? And if we can push the electrons there and do that, this reaction should work, right? No. What's the problem here? This does not work. All these charged simple nucleophiles we've been talking about with alcohols don't react at all. No reaction. Either primary, secondary, or tertiary. What's the problem here? How good of a leaving group is that? Well, it's OH minus. You might think electronegativity, it's okay to have that negative charge on oxygen. What about basicity? That comes from water, right? pK of 15. So that's a super strong base compared to the halides, right? We had halide leaving group. Those are great because X minus is fine, comes from a strong acid. But here we don't have any reactivity. And this is kind of peculiar, I think, because alcohols are some of the most common functional groups in biological molecules, right? They're in amino acids, they're in sugars, they're in nucleic acids, DNA, RNA. They're all over the place in metabolites. You'll see in metabolism. Alcohols are very abundant, but they're not good leaving groups. We can't easily functionalize them. We have to convert them first in the presence of acid or a catalyst to hydronium ion. Okay? And so the simple reactions we'll do here in chapter 9, most of these will involve strong acid. converting the alcohol into a better leaving group now. Why is it a better leaving group? Well, now you can imagine a nucleophile coming in and what? Displacing this, getting the product, and what's our byproduct here? It's alcohol or it's water, right? So by protonating this, and we can either do this with strong protic acid, we'll see with hydrochloric acid or the HCl, HBr, or we'll see later on when we get into the biological reactions. This is done with an enzyme, right? So a catalyst, an enzyme can convert that into a better leaving group. So why? Why has nature selected alcohols to be a very common functional group, yet they're not very reactive? Well, I think it comes down to a control issue, right? You want to control reactions in a certain way. You don't want all the molecules in nature to fall apart spontaneously, right? You want them to maintain some stability and then react with certain nucleophiles or whatever reagent only under a very controlled way. So maybe a catalyst or an enzyme can do this and then trigger the reactivity only when it's needed. So I think it's a control issue, but it's a philosophical issue too. It comes down to how good of a leaving group is this. This is a terrible leaving group, right? Because it's too basic. This one's fine because this generates this non-acidic thing once it's protonated here. So the hydronium ion we'll see is a real key here in this chapter. Let's look at the outline. Let's get to what you actually need to know. Sorry. So we'll look at, the basic structures here. The OH group, it is bent. It's water-like. So you're already thinking about the solubility issue. Yeah, you can hydrogen bond all over the place, right? We'll do naming. The IUPAC thing, alkanol is the parent name now. OL is our prefix, so we take the E off the end of alkane. We'll still identify the longest parent, but the OH group always gets priority now. It's a prominent, important functional group moving forward, and it has priority over all the ones we've covered so far, the alkyl and the halides. Doesn't matter alphabetizing or anything. You always give the lowest possible number on the chain to the alcohol. We'll also do naming of ethers, alkyl ethers or epoxy alkanes. We'll do epoxy names too. Oxirane's the common name for that little three-membered ring, or alkene oxide, whatever. Hydrogen bonding, the dominant thing here for the properties. Branching has an effect there. We'll have to look at that for boiling point changes. Interesting compounds, I've already shown you some. We'll look at quite a few more. Preparation, already reviewed a couple things with SN2 and SN1 chemistry. So you already know how to make a lot of these things. Reactions, and again, hydronium ion will be the key leaving group. So here we go. Here's the reactions. Here's the new stuff you got to know, right? So dehydration, we can take an alcohol and treat it with strong acid. A lot of times we have to heat it up. Different condition variations here, but sulfuric acid, very strong acid, right? With an alcohol, we'll get the alkene product. That's called a dehydration reaction. Why is it called dehydration? Because you're eliminating water, the OH, and a proton here. That's the elements of water, okay? And that's an important transformation to go from an alcohol to an alkene, okay? Very important reaction. We'll see how that works. Also, toxic acid, it's an E1 type process. Tertiary is faster than secondary, faster than primary. If you have branching nearby here, this is kind of a corollary to the dehydration reaction. Branching, because it goes through a carbocation, I'm not showing the mechanism here, but we are down here. It does go through a carbocation. Once you protonate, form hydronium ion. This carbocation, if it's branched next door, it can have a shift, we call. An alkyl group with its pair of electrons can move over and form a more stable, in this case, tertiary carbocation when it started as a secondary carbocation. So we have to examine the structure. If we have branching at the adjacent position, we often see the shift process before the actual alkene is formed. We can do that dehydration or form the alkene using other reagents. that don't involve strong acid like phosphorus oxychloride and pyridine. That will form the alkene directly without a carbocation intermediate and without rearrangements. So that's a very useful reagent there. If we treat the alcohol with a strong HX acid, okay, so HCl or HBr, the halogen acids, they're nucleophilic enough where when the carbocation is formed, X minus is a good enough nucleophile to form the alkyl halides. With sulfuric acid, no, that's a non-nucleophilic thing. It's resonance stabilized. Sulfonate is not a good enough nucleophile to go on. But the halides, if there's nothing else in there, can form the alkyl halides. So that's really our second reaction, dehydration and halogenation or halide formation, okay, of alcohols. And we can also do that without the strong acid conditions. We can use thionyl chloride, SOCl2, to form alkyl chlorides, or phosphorus tribromide. And again, these go without rearrangements. The strong acid conditions will allow for rearrangements before halides form. But we can also do it under non-acidic conditions with these two reagents here. We can also convert the alcohol instead into a tosylate leaving group, and we'll show you how to do that from tosyl chloride. That becomes a very good leaving group like a halogen, and we can do all the SN2, E2 chemistry that we've learned before. So I kind of gave you a heads up previously on that. Now, ethers normally are very stable. You have to protonate those with very strong acid, HI or HBr, to get those to react. And they will form alkyl halides that way, okay? But that's really strong forcing conditions. Normally, we consider things like diethyl ether as inert. But if you have an epoxide, which is a little three-membered ring guy there, those do easily open up with mild nucleophiles. And they do SN2 type reactions and SN1 reactions if they're more substituted. So we'll see those. Some specific applications that your book mentions. And these application ideas can show up on the test. So don't just blow these off, but make sure you understand, the fundamentals of this and why we're showing you leukotrienes or these prostaglandin guys, because we're showing you some of these reactions that are involved that we're covering in this chapter. Benzopyrene, this is carcinogenic epoxide that's formed from soot from cigarette smoke. It's one of the best toxicology pathways where we know every step mechanistically and what molecules are involved, going from cigarette smoke all the way to lung cancer, which is an important toxicology, epidemiology type thing to be aware of, but involves mutation of this tumor suppressor protein, P53. And it all comes out of this little epoxide guy that forms on the soot molecule. So, there's connections all over the place here on this. But, yeah, let's get into this. Here's some more important molecules maybe to at least be aware of, or find the ether, find the alcohol here, ethanol. Yeah, and why do I say Hall of Fame here for ethanol? That molecule kills more people worldwide than any other, okay? Fatalities on the road due to drunk drivers worldwide, that's thousands of people. Cirrhosis of the liver and damaging health effects from drinking alcohol in excess. So, what's up with ethanol? Why would anybody want to drink that anyway? Well, it's a historical thing, right? It's a food preservation thing. If you look back at ancient peoples preserving their grain and their fruits, whatever, the fermentation, the yeast creates enough ethanol to be antibacterial to other microorganisms. So it's a way to preserve those things. And ethanol does have a pleasing effect on people. So it is a GABA inhibitor. Gamma aminobutyric acid is one of the sedation neurotransmitters in the central nervous system, and ethanol mimics that. And some people like that effect, but the damaging effects, and we know from the word of wisdom, how to deal with ethanol. But we need to be, I think, understanding of people around the world, especially the historical use of it. I think the really bad thing about ethanol is when it began to be distilled and increased the concentration of the ethanol in alcoholic beverages. So when that took over, then you had the really bad effects of drunkenness and whatever. But yeah, ethanol. We could talk a lot more about that if you want. Let's not, though. Okay. Epinephrine, there's a secondary alcohol. We got stereo centers here. This is a stimulant. This is from the Mawang plant in Asia. All of the cough medications and a lot of other drugs are based on this. If you add two hydroxyl groups here, that's epinephrine or adrenaline, right? Which is a neurotransmitter in higher animals. Diethyl ether, we talked about that, the analgesic compound. Taxol, a lot of alcohols and some ethers. And there's this little four-membered cyclic ether over here, which is interesting. So that's highly strained also, but you see it there. And then we got the epoxy resin guys, which is a diepoxide, reacts with a diamine to do the cross-link to form the epoxy glues, the resin materials, which are very strong adhesive materials. BHT is a food preservative, erythromycin's an antibiotic. We'll see more on the prostaglandins later. Periplanone, disparlur are insect pheromones. Diosgenin, from the deadly nightshade plant. It's used for heart medications. It has a very low LD50 value. It has to be used very carefully, but that will correct heartbeat problems. Very potent drug. It's related to the steroid compounds. It's just kind of interesting. Anyway, be aware of that. Be able to point out different factors there which might affect the properties of this compounds. All right, let's get into the naming here. What we need to know there, the IUPAC naming, alkanol. So we've got the parent and then the OL on the end. Now I've already pointed out that the alcohol always gets the lowest priority number, but again, you have to count it on the chain there. So something like this would be identify the parent chain first, right? Hexane, and then hexanol. Would be that. So, or hexyl alcohol, you could say, is a common name, but hexanol would be the IUPAC name. Is anything missing, though, on this name? Is that the name of that compound? What else do we need here? We need one, right? Is there such thing as 2-hexanol? Yeah, there sure is, right? 1, 2, 3, 4, 5, 2, 3, 6, and then it's 2 position. You'd have that, okay? Okay, so, it's always on the chain there, and the lowest number here being 2 for 2-hexanol. 3-hexanol is also known. Is there such thing as 4-hexanol? No, that's the same as 3-hexanol, right? So keeping track of that. By the way, these ones in the middle here are chiral, right? If we had a stereo center, we'd have to specify that as well. Okay, how about this where we got another substituent? And how do we handle this? Well, start with the longest chain here. 1, 2, 3, 4, 5, 6. It's also hexanol. And this is where you assign that number, the lowest possible number, to the alcohol at the beginning. And then all the other substituents are relative to that, okay? Which is kind of surprising because this is a 1, 2, 3 hexanol. It's not a 1, 2. You could say, oh, we've got a methyl to 2 position. That should be 2. That breaks the tie. That's the lowest number overall. No, now we have this priority rule with the alcohol getting the lowest possible number. So this is 3, 4, 5 methyl, 3 hexanol, okay? So the lowest number goes to the alcohol, okay? That's the difference now, I think, in the naming. And you see it in cyclic ones as well. So if we've got this guy, here we have, 1,1-dimethyl. We would have numbered that 1,1-dimethyl before, right? And then maybe 3 alcohol and then a 4 another methyl. But here, what do? This is cyclohexanol. And the cyclohexanol is number 1. In fact, we don't need to number that. It's implied here to be number 1. Okay, it would be redundant to put a 1 out here. Because on the cyclic alcohols, the alcohol is always number 1. Okay, and then how do we number here around? 1, 2, actually, 3, 4, 5. Okay, so if we went the other way, it'd be 3, 3, 6. Okay, that would be higher. So this is 2, 5,5-trimethyl. Sorry, it's probably too small to see that, but it's always implied there. All right, let's do a hard one here, maybe. And we haven't done any ones with stereochemistry yet. And maybe this will help you review for test 2 here a little bit. Let's see if you can do this one. Oh yeah, a lot of stereocenters. Okay, finding the longest chain there is important. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is a nonane, all, known and all, and 1, 2, 3, 4. And you assign that first. Okay, now everything else is relative to that. And what do you come up with? 3-chloro, I think. 8-fluoro. Is that way out there on the end? Yep. And then 6-isopropyl. Sorry, way too small, I know. 3-chloro, 8-fluoro, 6-isopropyl, 4-nonanol. Boy, there's a mouthful for you. Is that it, though? Oh, we got all these stereocenters, don't we? Okay, 1, 2, 3, 4. Yeah, the isopropyl group. I'll just summarize them here. 3S, 4R, 6R, 8R. So there you go. You can practice that. But alcohols are not on test 2, okay? You can practice your RNS there, but alcohol naming's not. But I think that's a very hard one. Takes a little bit of time to figure that one out. All right, let's look at diols. I've mentioned an important diol, which is this guy, ethylene glycol. Glycol, it's antifreeze material, has a very low melting point and a high boiling point and high heat capacity. So it's used in cars, engines, right, in the radiators to absorb the heat from the engine, then dissipate the heat to the outside. If you use just water in your radiator, it will boil over, right? So you got to add that stuff. And the problem is, it tastes like a sugar. Sugar molecules, every carbon has an alcohol on it, polyalcohols. And this one tastes sweet just like sugar. So in the old days, they started using antifreeze, ethylene glycol. A number of kids and dogs became exposed to this toxin. They'd take a drink of it in the garage, whatever, and it tasted sweet. So how do you deal with that? It actually has a pretty high LD50 value. You have to ingest a lot of it to have a lethal dose. But because it tastes sweet, dogs and kids would keep drinking it, whatever. So the solution is they added a compound called Bitrix, which is a super bitter tasting compound. So all of them now, and it's a highly colored compound now, so if it sits around in the garage, whatever, kid opens it up, it has this glowing yellow or blue color to it. You've seen antifreeze, any motor guys out there? Okay, so yeah, so that bitter compound is there to make people spit it out right away. But how do we name these? They're alkane diols. And you have the whole parent name there, and then you just add diol on the end, okay? And you need to have some numbers here, so X, Y, wherever the 2 alcohols are now, okay? So what would this one be? This would just be 1,2-ethane diol. Okay, how about this one? Let's jump ahead to one. Oh, and even one with some stereochemistry. So here we have what? Cyclopentane. And you draw out the whole pentane and then diol. And then, yeah, you need the 1,2 cyclopentane diol. And then you do need the stereochemistry here. You could say trans, but this one is chiral, right? So RNS there. I think this is the SS. Yeah. SS 1,2 cyclopentane diol. Okay. Would be that glycol version of that one. Okay, let's do ethers. Let's do them all together here. Ethers can be named a couple different ways. Alkyl, ether. That's actually a common way to name it, like diethyl ether is the historical analgesic agent. The other way is to name it alkoxy alkane. And here you have the longest parent hydrocarbon that we've done before. And then whatever ether groups, we call them alkoxy prefix names. And there you take the ANE off and you add OXY, okay? So methoxy, ethoxy, isopropoxy. There's some funny sounding names here, but we'll show you a couple here to get used to this. So you call it diethyl ether or just ethyl ether. That's really the common way. Or we've got a parent here, right? Ethane. When you get more complex, you have to use the IUPAC approach, okay? The simpler ones, you can use the alkyl ether. But what is this? Here's our new group here that we're calling what? An alkoxy group. And what alkoxy group is it? It's ethoxy ethane, okay? So this group right here is an ethoxy group. Ethoxy ethane, okay? No chemist calls it that. We call it ether, diethyl ether, or just ether. But that name takes over a little bit more. You can see when it gets a little more complicated, how you can name things here. So if you have something like this, how would you name something like that? So you have a long chain here. 1, 2, 3, 4, 5. So it is a pentane. And on the pentane, at the 1 position, we have a group here. What are we going to call that? Methoxy, right? And at the 1, 2, 3, 4 position, we have a methyl. Okay? And then we alphabetize them. So which one comes first, methyl or methoxy? And I think it is methoxy, right? Methyl has a Y right here. So methoxy comes first. And 4-methyl. Yeah, 1-methoxy, 4-methyl pentane. Okay? And that keeps track of naming that. Be too hard to name that as an alkyl ether, right? We'd have to summarize the two alkyl groups. But you can do that with this one. This is a simpler one. Here we just have 2 alkyl groups on the ether. So this is a methyl and a tert-butyl ether, right? In fact, that's the name for it, MBTE. Methyl tert-butyl ether, MBTE, is a common gasoline additive. Increases the octane number. It burns just like a regular hydrocarbon, but it's highly branched. So it actually burns very quickly and increases the octane number. But MBTE is actually an incorrect name. What you need to name here is alphabetizing. The methyl group actually is second in the alphabet. The tert-butyl group is alphabetized by the B, right? So actually the correct name for this, even doing the common name, is tert-butyl. And I'll get your question there. And then methyl ether. Okay? So that is the common way to name that. Question, or did that answer it? No, they're just mixed in with the regular groups. It's the alcohol that has the high priority group. Okay. But let's name this as a IUPAC name. So we need to identify the longest chain here, which would be a propane. Okay. And then what do we have on there? Methyl and methoxy. And again, we'd have to alphabetize correctly. Methoxy and then 2-methyl. You can see where the common name, tert-butyl methyl ether, is a lot easier to do than 2-methoxy, 2-methyl propane. Okay, but they're the same name there. Yeah, it's the alcohol that always gets the lowest possible priority. Alkoxys are just alphabetized in there. All right, let's do epoxide names. Um, epoxides are a little bit different because they are these strained uh, three-membered rings. The epoxy ethers, this internal bond angle here, theta angle, 60 degrees, right? That's a huge deviation from 109.5. That's what we'll see the reactivity. How are they named here? They're named as 1,2 epoxy alkanes. Okay, so wherever the epoxy group is here. So if you had this one, for example, what would you call that? 1, 2, 3, 4. So it's butane, epoxy butane. So you can see the parent is still featured prominently, the first thing to identify there. The two numbers are always right adjacent to each other if it's an epoxide. So in here you've got 1, 2, epoxy butane. Are we done with the name there though? No, it's stereo center right here, right? Hydrogen's the back, 1, 2, I think that's S, yes, S, 1, 2, epoxy butane. Yeah, that's probably enough. Yeah, I think you get the whole story there. You can easily do some of the other ones there. All right, let's look at the properties. The main thing is hydrogen bonding. When in doubt, invoke hydrogen bonding. That's usually a safe assumption, actually, when we talk about properties. Hydrogen bonding has to do with the intermolecular forces, you know, how volatile at the boiling point or melting point might be. And hydrogen bonding has to do with water solubility. So it's always a good default thing to think about there. How well can hydrogen bond has to do with solubility. And these smaller alcohols, are just fine. All of these are infinitely soluble in water, but not this one. Oh, I'll give you another one that's kind of intermediate here. Okay. Remember we said the cutoff was what, 3 grams in 100 mils of water make these soluble. So these ones at the top are all infinitely soluble. This one though, 9 grams per 100 mils is the limit. Okay. So it's not infinitely soluble, but we call that soluble. And this is that 5 carbon rule. If we've got 5 nonpolar hydrocarbon carbons on a polar group, it'll still be considered water soluble. So we could even add one more here, and this would drop down the number. It would be less soluble. But we'd still have 5 there. We'd be around the limit. We'd be about 3 grams per mil. Well, what about this one? How soluble is this one? Well, it's 0.05 grams in 100 mils. And so what do we mean by that limit? If you exceed this amount in 100 mils of water, this will oil out. This is less dense, so it will form a separate layer on top of the water. Okay, so and this one too, if you exceed that, the 9 grams there. All right, how about boiling points? And let me put them in a little different order here. It's an important property. Let's start with tert-butyl alcohol and sec-butyl alcohol and then straight chain alcohol. And let's talk about the boiling point. And of course, it's the same argument for boiling point. What? How well can they form hydrogen bonds to each other, right? So we'll need to look at this in a little bit detail here. So the boiling point of this tertiary alcohol is 83 degrees C. And on its own, you can't tell much there. It's pretty high, But water boils at what? Higher than that, 100 degrees C, right? A lot more hydrogen bonding in water than there is here. But this is an alcohol. It does hydrogen bond. It's tertiary. What about when we go to secondary? What do you say, higher or lower? Higher? Okay, good. 98 degrees. Now, why? Well, maybe we'll get the third one on here and then talk about this. So let's go to the primary one. And what do you say there? Higher still, right? 118. Quite a bit higher. Okay. And why? The primary is what? Less hindered than the tertiary. So when we talk about hydrogen bonding with itself, this is going to be a little more available, right? Than if we tried to do hydrogen bonding with this. Look, we're starting to get this happening, right? The more substituted or branched at that position is going to make it harder to hydrogen bond. They're going to butt right into each other, right? And this is a polar effect right here, partial negative charge, partial positive charge. And that's getting in the way of this hydrocarbon branching. So the more branched they are, the more volatile they are. Primary alcohols can do better hydrogen bonding. And in general, they're more soluble in water too. So it's a couple effects there too. Let's look at ethers. So if you looked at the boiling point of ether, that's 34 degrees. And why is it so much lower there then? Well, there's no hydrogen on the oxygen, right, to bond with itself. But what about its solubility? It is infinitely soluble in water. So it is a hydrogen bond acceptor, right? It can interact with water that way, but there's no hydrogen bond donor on it, okay? So it can't hydrogen bond with itself. So it's more like a regular hydrocarbon with a very, low boiling point, okay? So I think that summarizes it there. The problem with diethyl ether is it will eventually air oxidize. This is called autooxidation with oxygen. And these old bottles of ether, and this was a real bad effect that was found early on, the more of these peroxide type compounds that build up, that's a detonation hazard. So you not only have the high flammability of ethers, but you also have the ability to explode here, which makes them even more dangerous with these older materials. There are some polyethers to mention here. You can have what are called polyethylene oxide materials, which have ethers going down a chain in a repetitive manner. These are polyethylene oxide materials or PEG materials. You can have them as super long chains, and these are biocompatible polymers. These can be compatible with living tissue materials. A lot of surgeries repairing different tissues in the body use these PEG type polymers now. And you can see, it can hydrogen bond with water. It can be compatible with water in aqueous solution, but it's a covalent chain, which allows some rigidity and some usefulness there. So these biopolymers with the PEG materials. So let me show you one other polyether here. I think go into the overhead. Yeah, purple benzene. And there was a question. Did I not see someone's hand? Yeah, go ahead.
I was just curious, like if you have that diethyl ether dissolved in water, does that make it harder to distill the hydrogen bond?
Harder to do what?
Harder to like distill, like with the temperature at the higher than 34 degrees.
No, ethers generally are much lower in boiling point. So the question was the ethers?
Yes, it's just like the fact that it accepts hydrogen bonds, does that make it harder to distill? Like you have to raise it beyond
Yeah, the question is it hard to distill ethers? And I would say no. You looked at the boiling point of diethyl ether, it's like 34 degrees. All those other alcohols were up, well above that number. And that's because they're hydrogen bond donors and acceptors. The ethers are just what? Hydrogen bond acceptors. They don't have a hydrogen on the oxygen. So it's a little bit different there. They tend to be much more volatile. Yeah, but good question. Yeah, so know something about the properties there, solubility. I think the main thing of the alcohols is the branching. The more branching you have on an alcohol, the lower the boiling point, because hydrogen bonding is more difficult to achieve there. The primaries do hydrogen bond. This is another one to point out, just real quick. You can make these polyethers in a cyclic structure. These are called crown compounds for a good reason. You can picture that sitting on someone's head, I guess. Or you can picture a metal being coordinated right in the middle. These lone pairs are what Lewis bases, and they can point right toward a positively charged metal. So here we have potassium being in the middle there of this crown, 18 crown 6. 18 refers to the total number of atoms around the ring. 6 is the number of oxygens. Don't worry about that. You don't need to worry about naming them. Smaller crowns are known. They bind to smaller metals. A lot of selective effects. And one thing that's pointed out here is you can get these strong oxidizing materials like permanganate into nonpolar solvents if you add a crown compound. Now, potassium permanganate on its own is a salt material, right? Very polar. So it does not dissolve in benzene at all. This purple salt will just sit at the bottom of a clear benzene solution. But if you add in the 18 crown 6, look at this. You get this nice purple solution. Why? Because the permanganate, which is actually the purple color, is pulled into the nonpolar solvent because its countercation, the potassium, is now solvated. Why? Because now around the periphery you have the nonpolar ethers, right? And the alkyl groups there that point toward benzene. So that's a way to make what's called purple benzene, which is a strong oxidizing agent for different organic compounds. All right, let's go back to the board here and talk about the preparation of alcohols and the reactions. I've already done the preparations, the SN2 and SN1 type reactions. We've already talked about in general the reactivity of alcohols versus the other leaving groups that we've seen already. So the halides are very good leaving groups. The alcohols on their own are terrible leaving groups, right? Because of the hydroxide coming off as a strong base. That's not going to be favored, okay? So we need to turn it into something else. So to summarize the reactions we're going to do, let's use a simple alcohol like isopropyl alcohol. We can eliminate that. So this will be an E type of reaction. And we're going to use sulfuric acid or POCl3, okay? And we're going to go to the dehydration products, okay? These are the two different ones we're going to do. Here we're going to form cations. Here the elimination is going to be concerted. So the mechanisms are going to be different between sulfuric acid and POCl3 or POCl. Sometimes we call it POCl, phosphorus oxytrichloride. This one will go with rearrangements. So read ahead in the chapter for next time and see that because of the free carbocations, we have that shift possibility. Here, no rearrangements, okay? And that summarizes the reaction. Dehydration, that's the new reaction, okay? Going from an alcohol to an alkene. Now we can also take this and convert it with hydrochloric acid or hydrobromic acid to the corresponding halide, okay? We can halogenate alcohols, okay? And this will also go through a carbocation intermediate with the rearrangements of the shifts possible. We can also do this with thionyl chloride or phosphorus tribromide to get the corresponding chloride or bromide from the alcohol without rearrangements, okay? We say these type of conditions are complementary, okay? And we'll see here that this approximates what an enzyme does here. We're going to convert this into a better leaving group. And we'll see with the rest of the mechanism how we get to the alkenes, how we get to the halides, okay? But those are the key reactions we're going to learn here. It's going to, of course, depend on whether this thing's tertiary, secondary, or primary, right? And what the reagents are. And so examining, again, the structure and what these reagents are is going to help you out here. But yeah, read ahead. The next couple of class periods we'll be going over those reactions. Very good questions to this point. Okay. So naming and properties, I think we're okay there. Next couple times, though, we'll be heavy into the reaction. So very good. We'll see you next